In the previous videos, we looked at Archimedes' principle and the hydrostatic equation, but in those cases, the fluids were not moving. Now we are going to introduce dynamics in our fluids, but we are going to just use a very simple model just to try to understand some of the ideas. The ideal fluid that we are going to study is one that is incompressible. That means you cannot change the volume of the fluid. It is non-viscous, so there is very little resistance or no resistance to motion, and the flow is steady. You have laminar motion, laminar flow, like this one here, as opposed to a turbulent flow that, that you would get on this part. So these are our assumptions for the fluid, incompressible, non-viscous, and laminar flow. An important idea is that of a streamline, and if you think of the fluid as made up of particles, then the particles will move through a line like this one here, and those are called streamlines. They never cross. The the velocity of a particle is tangent to streamline at all times, and the speed is higher whenever you have more streamlines. This is a wind tunnel that is being used to study the aerodynamics of this car, and you can see the streamlines here as the car moves. Fluid dynamics requires what we are going to study requires of two equations. The first one basically says that if you have a fluid going in here, you have to have the same amount of fluid coming out. That is not going to disappear anywhere. That is a continuity equation. It just says that whatever comes in here have to come out here because there is no holes in between that would make fluid go anywhere else. So if you have 1 liter coming here, 1 liter should come out here. However, if this is narrower, then here is going to this liter is going to come faster than it comes out, than the velocity that it has when it comes out here. So let's look how that equation happens. So in this volume here, it's exactly the same volume here, and it's given by what? It's given by the area A1 times its thickness. This thickness is equal to V1 times delta T. So the volume here is V1 A1 times delta T. In the same sense, the volume here would be V2 A2 times delta T. And they have the same amount of fluid. So therefore, we can put the fluid that you have here have to be equal to the fluid that you have here. And we can put those two equations together and we get the continuity equation, the equation of continuity, which says that V1A1 is equal to V2A2. And all it's saying is that if you get a liter coming in here, you have to get a liter going out here. The other important equation, which is the one that we use to describe dynamics, is Bernoulli's equation. And Bernoulli's equation is basically conservation of energy. So suppose that you have a fluid coming in here. So that fluid has some potential and kinetic energy, right? So the fluid is going to come out here. And here is going to have some potential and some kinetic energy. Now so let's say you have K1 plus U1, potential plus kinetic energy here, and then you have K2 plus U2, right? Plus K2, right? So this is the energy here and this is the energy here. The difference between the two have to be equal to the work done by the pressures, the work done by the external agents, which is the pressures. If we put those equations together, we get basically this is the kinetic energy, this is the potential energy of one, this is the pressure of one, this is the kinetic energy, this is the potential energy, and this is the pressure. We can rewrite this as 1/2 rho V1 square and then plus rho G Y1 right? So this is potential, kinetic plus potential at 1 minus 1/2 rho V2 square plus rho G Y2. Okay, this is kinetic plus potential at 2. That has to be equal to P2 minus P1. And this is basically the work per unit of area done by the, the system. So let's look back at this picture here. So the work done here is the force times this delta x1, and the work done here is the force F2 due to the pressure times delta x2. What is this force F1? Well, F1 is equal to P1, the pressure here, times A1 times delta x1. And here you get that F2 is equal to P2 times A2 times delta x2. So, and this, well, this is the force, this is, sorry, this is W and this is W. This is the force here, F1, and this is the work done by this force at this point. And here, this is the work done by this force at this point, right? And when you put these two equations together, then you get Bernoulli's equation, which allows us to work with some simple fluids. Another alternative expression is that P plus the kinetic energy plus potential energy, pressure plus kinetic plus potential, is always a constant. Thank you.